Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
Imagine for a second, just, close your eyes and imagine you are an ancient shepherd.
Okay, I'm with you.
You own 100 sheep, and that is your entire world.
Sounds pretty peaceful, honestly.
Right, but in your whole lifetime, you will never, ever need to count to 145, let alone, figure out how to write down 10,000.
Yeah, I mean, why would you? There's no point.
Exactly, so why would you ever bother inventing a number for it? Welcome to the deep dive.
Glad to be here.
Today, we're doing a bit of a peer-to-peer learning session. I'm taking on the role of the student today, throwing questions and probably, a few wild guesses at the wall.
I am fully prepared for the wild guesses.
Good, because you're taking the lecturer seat.
Oh.
You're going to walk us through how humanity was quite literally forced to invent complex math.
Yeah, I will gladly take the lecturer role today, because the history of how we learn to count, it isn't just about numbers, It's about crisis.
Crisis?
Yeah.
Really?
Oh, absolutely. The math we use today didn't just fall out of the sky. It was engineered out of sheer panic when early civilizations started growing too fast.
Okay, I love that framing. So where are we getting this from?
For our guide today, I've pulled section 4.2 of chapter 4 from Contemporary Mathematics.
Awesome.
We're going to look at 3 distinct civilizations, the mathematical walls they hit, and the wildly different ways they tried to, climb over them.
All right, well, I'll bite. If my hypothetical shepherd only needs to count to 100, what is the crisis that suddenly demands bigger numbers? What actually changes?
It's all about complexity. I mean, as long as you're just tracking your own sheep, knowing the difference between 1, 2, and a whole bunch, that works fine.
Right, I have a lot of sheep.
Exactly. But as section 4.2 points out, as soon as a society develops widespread commerce, as soon as trade routes cross borders, and crucially, as soon as a ruler decides to raise a standing army of thousands.
Oh, wow. Yeah.
Right, humanity hits a wall. You can't just eyeball payroll for an army.
No, I imagine they'd get pretty mad if you shortchanged them.
Exactly. And you can't just tally marks on a stick for grain shipments that feed an entire city. The primitive systems just cracked under the pressure of those massive quantities.
So essentially the software of human thought had to be upgraded to handle the new hardware of city-states.
That is a great way to put it, yeah.
So who was the first to push that update?
Well, we have to look at Mesopotamia, the Babylonians.
Okay, Babylonian.
The textbook includes this great image, figure 4.3, of a Babylonian clay tablet. This is where math was literally pressed into the earth.
Right, because they didn't have paper.
Right, they used a stylus to press marks into wet clay. But, and here's the massive challenge they faced, they didn't have 10 digits.
Wait, what do you mean?
Well, our modern Hindu-Arabic system, it gives us 0 through 9, right? So we can build any number we want.
Right.
The Babylonians had to build their entire mathematical universe using exactly 2 symbols.
Wait, just to, like binary code.
Not quite binary, but, close in its minimalism. They had a downward-pointing wedge,
Okay.
which represented the value of 1, and they had a left-pointing chevron, which represented the value of 10.
A wedge and a chevron. That's it.
That's the entire toolkit. So for anything up to 59, they used an additive system. You just stamp those 2 symbols into the clay.
That sounds incredibly tedious.
Oh, it was.
I mean, if I want to write the number 59, I'm pressing 5 chevrons and 9 wedges into a piece of mud.
Yep, 5 10s and 9 1s.
That's 14 distinct marks for a 2-digit number. If I'm a scribe calculating a month's worth of grain, my tablet is going to look like a cluttered, smudged mess.
You're touching on the exact friction point that forced their next innovation. You're completely right. An additive system is a terrible way to scale.
Yeah, quit.
A lot of scribes probably wanted to. So when they hit the number 60, the Babylonians did something revolutionary. The system transformed from additive to positional.
Positional. By positional, you mean like how we use columns.
Exactly.
Like we have a ones column, a tens column, a hundreds column. Depending on where the digit sits, its value changes.
That's the concept, yes.
Right.
But here is where you have to temporarily forget everything you know about math.
Uh-oh.
The Babylonians didn't use powers of 10. Their positional system was base 60.
Base 60. Wait, so instead of a tens column and a hundreds column, they had a ones column and then a 60s column.
Correct. And the next column over isn't thousands, it's 3600s, because it's 60 times 60.
Wow.
So if you place that single downward wedge, the one that usually just means 1, into the second column, it suddenly represented one group of 60.
That seems entirely unhinged.
I know, right?
I mean, we have 10 fingers. Base 10 makes biological sense. Why on earth would an early civilization pick 60 as the foundation of their math? It feels so arbitrary.
It sounds completely arbitrary to us, but mathematically, it is arguably superior to our base 10 system.
Wait, really? Superior?
Yeah, it comes down to fractions and division. 60 is what mathematicians call a highly composite number.
Okay, composite meaning?
Meaning it divides easily. Think about the number 10. You can only divide 10 evenly by 1, 2, 5, and 10.
Right.
If you have 10 sacks of grain and you need to divide them evenly among 3 workers, you're stuck. You get 3.333 sacks. It's messy.
Right, you have to start dealing with fractions and remainders, which I imagine is pretty tough to carve into wet clay.
Extremely tough. Now look at 60. 60 can be divided evenly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30.
Oh, wow. That's a lot of options.
Right. If you're a Babylonian merchant trying to divide shipments of goods or plots of land or payments, base 60 is a dream. It practically eliminates the need for complex fractions in everyday trade.
That is a massive aha moment for me. It wasn't arbitrary at all. It was hyper-optimized for early economics.
Yeah.
I never thought about how clunky base 10 actually is for division.
It's so hyper-optimized that it never actually went away.
What do you mean?
The Babylonians gave us the 60-second minute, the 60-minute hour, the 360-degree circle.
Oh my gosh, you're right.
Every time you look at a clock or a compass, you are navigating the world using Babylonian base 60 math.
That's incredible. We're still using their software.
Exactly.
But hold on, I have a logistical question. If they are using columns like moving a wedge to the left to turn it from a 1 into a 60, how did they keep the columns straight? Because we use lines on paper, but on a wet clay tablet, if a scribe is a little sloppy with their spacing, how do you know which column a symbol is actually in?
You've just stumbled into the most dangerous flaw in the Mesopotamian system.
I knew it.
Yeah, it sets the stage for one of the greatest conceptual leaps in human history. For most of their history, you see, the Babylonians lacked a 0.
Here's where it gets really interesting. Because not having a 0 sounds like a catastrophe for a positional system.
It was a disaster waiting to happen.
It's like typing on a computer keyboard that doesn't have a space bar. I mean, if I want to write the number 3601, which in their system is 1 in the 3600s column, nothing in the 60s column, and 1 in the ones column, how do I signify that the middle column is empty?
The short answer is, early on, they didn't.
They didn't.
No, they just had to rely on context, which, as you can imagine, caused terrifying accounting errors.
I bet. Did you owe me 1 sheep or 60 sheep?
Exactly. So later on, scribes started leaving a physical gap, literally just an empty space on the clay, to imply an empty column.
But a blank space isn't a number, it's just nothing. Why didn't they just invent a symbol for 0 from the start?
Because 0 is intensely counterintuitive. The textbook has a great "Who Knew" segment on this very thing.
Oh, I read that part.
Yeah, we take 0 for granted.
Yeah.
But conceptually, it's a massive philosophical hurdle. If you walk up to a farmer in the ancient world and ask how many cows are in an empty field, he doesn't say, "I have 0 cows."
Right, he just says, I don't have any cows.
Exactly. Emptiness was viewed as a state of being, not a numerical quantity. You don't count what isn't there.
So the idea of giving nothing its own dedicated symbol just didn't compute with human logic at the time.
Right. It was the invention of positional columns that literally forced humanity to invent 0. They absolutely needed a placeholder.
Wow. Necessity is the mother of invention.
Truly. And this need was so universal that 0 wasn't just invented once. It's a prime example of convergent evolution.
Meaning different people figured it out independently?
Exactly. A 0 symbol eventually appeared in Mesopotamia. It was also developed in India in the 400 CE, which is the ancestor of our modern system.
Okay.
But it was also independently invented by the Mayans around the 4th century CE.
Okay, let's pivot to the Mayans, because this is fascinating. If they invented their own 0, did they use columns like the Babylonians? Section 4.2 shows they didn't use wedges, they used dots and bars.
Right, so a dot is a 1 and a horizontal bar is a 5.
So they used columns too.
They did use columns, but they stacked them vertically instead of horizontally. And instead of base 60, the Mayans used a base 20 system.
Base 20. So, as I mentioned earlier, base 10 makes biological sense with our fingers. The Mayans just, included their toes?
Basically, yeah. So their place values started with the 1s, then the 20s, then the 400s, which is 20 times 20.
Makes perfect sense. It scales up predictably.
It does, until it hits a very specific cultural roadblock. The Mayans actually broke their own mathematical rules for one massive exception,
Oh.
their calendar.
Why break the math for a calendar? Why not just use the normal base 20 system to count the days?
Because the Mayans were arguably the greatest astronomers of their era, and their entire civilization revolved around the solar year.
Okay.
If they used strict base 20, their third place value is 400. But a solar year is about 365 days.
Right.
If they used a 400-day mathematical cycle to track the seasons, their agricultural calendar would be out of sync with the actual sun by over a month every single year.
Ah. That's a fast track to planting crops in the dead of winter and starving to death.
Exactly. It would be devastating. So
Ugh.
they engineered a workaround. In their calendar math, they tweaked the third place value.
Tweaked it how?
Instead of multiplying 20 by 20 to get 400, they multiplied 20 by 18.
Oh. Okay, let me do that in my head. 20 times 10 is 200. 20 times 8 is 160, so 360.
360. Suddenly, their math aligns beautifully with the solar year.
Wow.
By just altering one column in their positional system, they hard-coded the movement of the Earth around the sun into their daily arithmetic.
That is undeniably brilliant. But wait, a solar year isn't 360 days, it's 365.
Right.
If they lock their math into a 360-day cycle, what did they do with the 5 leftover days?
They added them at the very end of the year, and this is so interesting. It created immense cultural anxiety.
Anxiety?
Why? Because these 5 days, which were known as the Wayeb days, sat outside the perfect divine mathematical harmony of the 360-day cycle. So the Mayans considered them profoundly unlucky.
Oh, I see. It didn't fit the math, so it must be bad.
Wayeb was associated with a god of misfortune.
Yeah.
During those 5 days, people avoided leaving their homes, they didn't wash their hair, and they essentially just held their breath.
You're kidding.
No, they literally believed the barrier between the mortal realm and the underworld was dangerously thin during those 5 days.
That is wild. It really drives home that, to them, numbers weren't just abstract tools for accounting. Math was the structural integrity of the universe itself.
Beautifully said.
So when the math didn't divide perfectly, they literally thought reality was glitching out.
Exactly. It's a
Yeah.
perfect encapsulation of how culture shapes math, which actually brings us to the ultimate contrast.
Okay, lay it on me.
We just discussed the Babylonians and Mayans, two civilizations that developed complex place values, columns, and zeros to understand the cosmos and run their economies.
Right.
Now, let's look at an empire that conquered the known world, built massive aqueducts, managed sprawling trade routes, all while stubbornly refusing to invent place values and absolutely rejecting the concept of zero.
Oh boy. So positional math and zero solved the problem of huge numbers. But what if a civilization didn't care about complex math and only cared about building an empire and paying soldiers? That brings us to the Romans.
Precisely. The Roman numeral system is incredibly famous, but mathematically, it's a brute force approach.
Very Roman of them.
Right. They use specific letters to represent set values. I for 1, V for 5, X for 10, L for 50, C for 100, D for 500, and M for 1,000. No columns, no zero.
See, I know the basics of Roman numerals from, reading the copyright dates on old movies.
Right.
But practically speaking, this seems like a massive step backwards. I mean, if I want to calculate a legion's payroll and I'm trying to multiply combinations of X, L, and C without any place values, that's a nightmare. Did they actually do long division with these letters?
No, they didn't. And that is the crucial missing piece that most people don't understand about Roman numerals. It is nearly impossible to do complex arithmetic on paper with this system.
Well, yeah.
So the Romans didn't try. They used a counting board or an abacus.
An abacus, like with the little sliding beats.
Similar, yeah. They used small pebbles called calculi.
Wait, calculate, is that where we get the word calculate?
It is.
Oh, that's so cool.
Yeah, so they moved these calculi around on a grooved board that represented different values. The actual math was physical.
I see.
The Roman numerals you see carved into stone were never meant to be a tool for calculation. They were just the receipt.
The receipts.
Exactly. They're just a way to record the final answer once the physical pebbles had done the real work.
Oh. So the written system wasn't the calculator, it was just the printer.
That's a perfect analogy.
That makes so much more sense. But still, even as a receipt, the way they wrote it is so clunky. If I want to write the number 4, I write IV, right, 1 before 5.
Yes, to save space, they developed subtractive rules. Instead of carving 4 individual lines, which takes up room, You put a smaller value before a larger one to indicate subtraction. So IV is 4, IX is 9. But the textbook highlights how strict and complicated these rules actually were. You couldn't just subtract anything from anything.
What do you mean? If I want to write 49, can I just write IL1 before 50? That's 2 letters. Super efficient.
It's logical, but it violates their rules.
Of course it does.
The letter I could only be subtracted from V, or X. You were strictly not allowed to subtract it from L.
Oh, come on.
So to build 49, you had to break it into chunks. First, you need 40, which is X before LXL.
Okay.
Then you need 9, which is I before X. So 49 is XL9.
XL9. That is practically a cryptography puzzle just to write down a price tag. It's so rigid.
It is rigid. And the rules continue. X can only be subtracted from L and C. C can only be subtracted from D and M. And subtraction always happens at the very end of a grouping.
This sounds exhausting.
Let's test you. If you look at the number 290, you write the 200s first, right? CC.
Okay, CC.
Then you write the 90, which is 10 before 100, so XC.
Put it together. CCXE.
Exactly.
CCXE.
It's so statuesque. I mean, it feels less like a fluid language of mathematics and more like an architectural choice. It's meant to be carved into a monument and just stay there forever.
That's the absolute perfect way to look at it. And it explains the legacy of Roman numerals mentioned in section 4.2.
How so?
Because it was so deeply tied to the monumental architecture of the empire, it survived long after the Roman Empire fell, and long after we adopted the vastly superior Hindu-Arabic system for actual math.
Oh, I see.
We still use Roman numerals on the cornerstones of important buildings to give them an air of authority. We use them for monarch titles like King Charles III.
And, of course, the most American monument of all, the Super Bowl.
Yes. The Super Bowl continues to use Roman numerals, which is just a fascinating quirk of modern pop culture, keeping a dead numerical receipt system on life support. All right. Stepping back from all the details, the through line here is just incredible. We've gone from Babylonian scribes dividing grain with base 60 wedges, to Mayan priests tracking the solar year with a newly invented zero, to Roman engineers using pebbles to do the actual math while carving those rigid letters into stone.
It forces us to realize that numbers are not universal laws waiting to be discovered. They are distinctly human tools.
Yeah.
They are engineered, they are modified, and sometimes they're compromised to solve very specific cultural problems. Whether you are maximizing trade efficiency with base 60 or altering your place values to appease the gods of the calendar, the math you use is entirely shaped by the world you live in.
It really makes you look at the digits on your keyboard differently. We just assume our current 10-digit base 10 system is the ultimate final form of math. But history shows it's just the latest iteration.
Which is exactly the thought I want to leave us with today. The textbook makes it clear that ancient societies were forced to invent new math when their societies scaled up and their old tools broke.
Yeah.
Well, look at our current trajectory. We are moving into an era of quantum computing, where states exist in superposition. We have artificial intelligence processing data sets so large they frankly defy human comprehension. We are tracking deep space phenomena to cross distances that make our current numbers look, well, quaint.
So we're essentially the ancient shepherds suddenly staring at an empire.
Exactly. So the question we really have to ponder is this. Will our current Hindu-Arabic number system, with its neat little base 10 columns, eventually hit a wall?
Wow.
Just like the Babylonians who realized their little wedges weren't enough? Will we soon find ourselves forced to invent an entirely new, currently unimaginable way to comprehend the universe?
That is a staggering thought to end on. I mean, if you ever invent a new base system for quantum mechanics, let me know.
I'll be sure to text you.
Until then, thanks for guiding us through the history. And to you listening, thanks for joining us on this deep dive. Keep questioning the everyday things around you, even the numbers.